Hi, good evening, everybody. Tom, K3YH, and Roll, K3RA. We're going to do about an hour and a half of review of some of the mathematical calculations that are on the general class exam. So, welcome to all, and I'll turn it over to Roll to start out.
Okay. Hello, everyone, and hope you have a happy new year. Um, we are getting close to the end of our course. This week, this Thursday, will be the last one, and I hope if you're interested in taking the extra course that you're signed up already. If not, you know how to do it. Get my email, and I'll sign you up. The first thing just to remind you, we're going to go over the questions that have math calculations in them. There are a fair number that do. Um, so we'll try to cover all the questions that refer to math. And the first thing I want to do, let me share my screen here. Always an exciting adventure trying to get my screen shared correctly. Um, okay. It says participants can now see your screen. Happy New Year, as we say on the air. Okay, so
Yep, yep.
first thing I
We
want
can see it. It looks good.
to okay, great. The first thing I want to talk about a little bit is the metric system. And by the metric system, what I really mean is those prefixes that you're so aware of. They go tera, mega, kilo, units, milli, micro, nano, and pico. And there are more on each side. They go on to cover the biggest numbers you can possibly think of and the smallest numbers you can possibly think of. In fact, probably smaller than anybody's been able to think of yet. They got names for. But we're not going to worry about any of those. Remember, units are one and kilos are thousands. So I'm just going to say thousands because too many zeros. That's why we do this, to get rid of all these zeros that don't mean anything much. I mean, they're important because they tell us how big it is, but they aren't needed for the actual exact value or the close enough value. Let's put it that way. And mega is millions, and tera is billions, and milli is thousandths, micro is millionths, nano is billionths, and pico is trillionths. I have a THS. So if we put these in powers of 10, this is 10 to the 0. Anything to the 0 is always 1. This is 10 to the third. It means 1 followed by 3 zeros. I'll just do it for this one. 3 zeros. And millions is 10 to the 6. That would be 1 divided by 6, followed by 6 zeros. And billions would be 10 to the ninth, or 1 divided by 9 zeros. And then these go the other way, 10 to the minus 3. Remember, that means 1 over 1,000, which is 0.001. 10 to the minus 6 is millionths. 1 over a million, which equals 0.00001. And 10 to the minus ninth, and 10 to the minus 12th. And the symbols for these, just quickly, capital T, small k. There isn't any symbol needed for that. Small m, Greek M, micro, and nano is N, and pico is P. You should be able to reproduce this chart. You don't need it for the exam, however, because there's only one question that really involves making this conversion. So I don't want to spend very much time on this, but it's something that generally you just should know how to do this. Remember, we gave you this saying, terribly Oh, I did this wrong here. This is giga, and this is sorry. This is giga, and then there's tera, not TERRA. So it's thousands, millions, billions, trillions. This is 10 to the 12th. And we generally don't go beyond gigahertz, but this terahertz is up in the light frequencies, actually. So the expression for this is terribly gigantic monsters kill 1 million men napping peacefully. I guess I can write that. It'll take longer to write it out than it's worth, probably, but terribly gigantic monsters kill 1 million. Now this is a little confusing because we're only talking about the milli here. Men napping peacefully. This, if you can't remember the order they go in, that's it. Now, what question comes up with that we would need this for in the extra class? It's G5CO8. G5CO8. G5CO8 is a pretty simple question. It says, what is the equivalent capacitance? Excuse me, that's not right. Oh yeah. It's not that easy. What is the equivalent capacitance of two 5 nanofarad capacitors? So it's two 5 nanofarad. So that's down here, nanofarad capacitors, and one. I'll use a different color for that. And one. I gotta close it off because I keep hitting it. Wait a minute. And one 750 picofarad capacitor. So here, whenever we do problems, we can't add, subtract, multiply, or divide unless the units are the same. So we can't add or divide with picofarads and nanofarads. We have to use just one unit, and the questions give you your choice in picofarads only. So picofarads are down here. So we have to convert 750, 5 nanofarads to picofarads. Now, the thing to remember is that when we're going this way, we shift 3 places to the right. And when we're going this way, we shift 3 places to the left for every step. In other words, we're going to have more of the smaller things as we go down. We're going to have more if we measure it in little things than if we measure it in big things. We're going to have more pounds than tons. We have 1,000 pounds, we only have a half a ton, right? So that's what we're doing here. We're going from nano to pico. We shift 3 places to the right. So we have to change this to 5,000. Whoops, I can't write. To 5,000 picofarad capacitors. It's the same as 2 5 nanofarad capacitors. Now, Tom is going to tell you how to do this calculation later, so I'm not going to take the time now to make this calculation of what's the total capacitance of 2 5 nanofarad capacitors in parallel. Is it in parallel or series? G5CO8s. Well, they're in parallel. So it turns out this is really pretty easy. All we have to do is add them together. But he'll talk to you about that. But now we can just add them. So it's going to be 10,750, because we're going to have 5,000 plus 5,000 plus 750. That's the key to getting this question right. That's the only question that I could find anywhere on the exam where you had to convert these units. There are many places where units are given to you in nanofarads and picofarads and microfarads and milliamperes, and you need to, and megahertz and kilohertz. All those things are given to you. But I don't think there's any need for doing these conversions any place except in this one question. I may be wrong about that, but I took a pretty good look. So again, if you're going from megahertz to kilohertz, there 1,000 times more kilohertz than there are megahertz in something. If it's X number of megahertz, it's 1,000 times that in kilohertz. And then if you go to units, it'd be another 1,000, because to go from mega to units would be 1,000, and 1,000 would be a million, and we know a mega is a million. Okay, terribly gigantic monsters kill 1 million men. Napping peacefully tells you tera, giga, mega, kilo, and then you have to remember milli for millions. Men is micro, napping, and nano, and peacefully. All right, so this is worth spending time on, even if you don't worry about having it on the exam. Any questions?
So far, no questions.
Okay. So, with no questions, the next thing I want to talk about is the dreaded decibel. There are lots of questions on the exam that mention decibels, but there aren't very many that require that you do anything with them, but sort of know what they are. So I'm going to tell you that if you're interested in knowing about how to calculate them in terms of logarithms and how to go from ratios to logarithms and logarithms to ratios, that's all in your book, and it's a great thing to know, but you don't need to know it for this exam. All you need to know is that dBs are a ratio of power. And a ratio of 2 to 1 is 3 dB. And a ratio, in fact, that's really all you need for the test. And a ratio of 10 to 1 is 10 dB. Note that it turns out that 10 to 1 is 10 dB, but 2 to 1 is not 2 dB. 2 to 1 is 3 dB. And if it's minus, it's the reverse. 1 to 2 is minus 3 dB. And of course, 1 to 10 is minus 10 dB. And that when you multiply, you add dB. So 4 times would be the same as 2 times 2 times, which is equal to 4 times, right? And since this is 3 dB and this is 3 dB, we add them, and so 6 dB is 4 times. Now, the only question you have is, how many dB is a factor of 2? And as Tom and I keep saying, 3 dB is a factor of 2. There are more problems than that. One problem is question G4D05. It says, and you need to know something about dBs to answer this. It says, what does the signal report of 20 dB, whoops, not 2 dB, 20 dB over S9 mean? 20 dB greater than S9. What does that mean? Well, 10 dB is 10 times, so 20 dB is 100 times. 10 times 10 times equals 100 times, and that's the same as 10 dB plus 10 dB. That's not 70, that's 10. Equals 20 dB. So 20 dB is 100 times. That's the question G4D05. And then Question G4D07 wants you to know, I'll put this number over here just for your info, G4D05. And G4D07 wants you to know that 1S unit, that is a unit on your S meter, is equal to 4 times power ratio. And if you go from S8 to S9, you go up by a factor of 4 power. If you go from S8 to S7, you go down by a factor of 4 power. What is a factor of 4? A factor of 4 is 6 dB, right? A factor of 4 times is 6 dB. So 1 S unit is equal to 6 dB or 4 times. Let's look at another question here real quick. A G4D06 just says this is G4D06. It just says how many dB is an S unit, and that's 6, so you know that. Question G8C15 wants you to know something about signal reports in FT8. And a signal report of +3 means that you have a signal to noise ratio of 3 dB. And it's in a bandwidth of 2.5 kilohertz, which I'm not going to go into right now. But +3 means 3 dB. That's a factor of 2. When we talk about antennas, we talk about the ratio of, we talk about dBi and dBd. This is dB relative to isotropic, meaning something that radiates in all directions. Isotropic, and this is relative to a dipole. And it points out that the dipole has 2.15 dB I. In other words, a dipole has 2.15 dB gain over isotropic antenna. That's because, remember, my balloon pushed that sphere out into kind of a bulge, making it into a donut shape, which gives it a little bit of gain in the maximum direction. The isotropic has no gain in any direction. It's the same in all directions. Gain is a ratio, and there's nothing with lower gain than isotropic because it radiates the same in every direction. And anything other than isotropic has some gain in some direction. So 2.15 dB, how big is that? Well, you don't need to know exactly, but it's not as much as 2 to 1, because 3 dB would be 2 to 1, so it's a little bit less than 2 to 1. Question G9C09 says that when you stack 2 dipoles together, you have 3 dB gain. Well, that makes sense. You got two Yagis rather stacked together. If 2 Yagis are stacked, they're going to be twice as much gain roughly. That's 3 dB. 3 times 3 dB is a factor of 2. G9A06 talks about the feed line loss is in dB per 100 feet. So that's, it's 3 dB per 100 feet would mean that half the power is lost per 100 feet. All right, again, to pass the test, you're going to need to know just 2 things. This. And that when you multiply ratios, you add dB. Any questions on it? That's all I intended to say on dB. Any questions?
Any questions? Put them in the chat window now. Looks like we're good.
All right.
Oh, wait a minute. Hold on. Sorry, I missed a question here. So, what's an S unit? Can you describe the just briefly, the S unit is a measurement of the receive strength.
Right. We talk. It comes out of the readability, strength, and tone system, which for CW has three numbers, and for phone has two: readability and strength. The first one goes from 0 to 5. The second one goes from 0 to 9. So theoretically, the strongest, most readable signal you could have on phone would be 5.9. Your signal report is 5.9, we would say. It can't be any better than that. S9 is what we call the signal report for strength. R5 would be the signal report for readability. Now, that's how it started, is just my feeling is that given that there's a scale from essentially 1 to 9, because 0 would mean I can't hear you at all, so how could you be talking to them? So there's a scale of 1 to 9, you're a 9. That means you're pretty darn loud. Now, they've converted that to a meter that you could read on your receiver, and they mark that from 1 to 9. And it turns out a lot of signals are even stronger than 9. Well, every step from 1 to 2, 2 to 3, to 3 to 4, etc., is a step of 6 dB. And if you remember what I said, that's a factor of 4. 3 dB is 2, so 6 dB is 4. So when you get to the top of the scale, S9, if you want to go further than that, you can only talk about the dB. There are no more S units. The S units themselves are dB. Each one stands for 6 dB. After that, you don't say your S units, you don't say S10, you say how many dB stronger than S9, because that's what's on your meter. And typically it's in tens. So 10 dB stronger, 20 dB stronger, 30 dB stronger. That's 10 times, 100 times, 1,000 times. Does that answer your question?
Yes, thanks.
Okay. I can stop now and stop my share.
You can kick back and relax.
I'm kicking back.
All right. So while I'm talking, you can, if you have questions, you can send them in chat to roll K3RA in the chat, and then he can interrupt me to talk to discuss your questions. Okay, I'm going to do two things here. I'm going to switch my camera.
It says I'm RK. I don't know because I said
I,
I'm roll K3RA, so it thinks I'm RK.
I don't. Oh yeah. Well, that's in the chat window probably.
Yeah.
Yeah. Okay. Funny. Um, all right. So there's the tablet, and I want to spotlight that so you all can see it when I write. And then I need to be able to share my screen. Okay, you should be seeing question G5B04
Yes.
and the ARRL practice exams. Okay, so let me tell you, the first thing I'm going to do is cover about 5 questions that are associated with calculating power. So this is the first, and I'm covering them mostly in the sequence they're in the book. So if you're looking in the book, this is on page roughly 4-2 is where they cover this particular problem. Somebody asked me, is this section, is this part of the book? It's spread throughout the book. So we don't have a math review chapter in the book. They're spread throughout. But most of the questions we're going to work on here are in chapter 4. So if you're looking in the book, this is in the neighborhood of 4-2. And the question is, how many watts of electrical power are consumed by a 12-volt DC light bulb that draws zero point 0.2 amperes? And important that this is DC power here on this particular question. So, here's the choices: 2.4, 24, 6, 16. And what I'm going to do is switch over to my tablet and show you how we calculate this. Okay, so let's just I always like to draw the picture. When you're taking the test, you don't necessarily need to do this, but here's my schematic for a battery, and that's 12 volts. And it's just going around through a light bulb. You draw it like that. And they tell you that the current going through this is zero point 0.2 amps. Okay. So this is the most straightforward thing. You draw your pie chart, P, O, I, and E. Okay. Remember how to draw this. You don't have to remember formulas. Ooh, look at that. I've got this auto zoom thing on the computer. I probably might want to turn that off. Um, so in this case, they've asked us to calculate what's the power. Okay. And we know the current and we know the voltage. And so you draw your chart, you cover up what you're trying to calculate, which is the P for power, and that tells you here on the pie chart that power is equal I times E. So in this case, power equals I times E. And hang on, let me just turn this auto zoom thing off a minute. Unfortunately, video settings. It's something in your video settings called auto framing. If you're a zooming person, then you need to know that. Okay, and I'll go back to full view. Okay, so you're seeing my whole pad now roll.
Yeah.
All right. Okay, so again, using the pie chart, I know P. I'm sorry, I want to calculate P, so it's I times E. So in this case, the I is zero point 0.2 amps and the E is 12 volts. So that equals 0.2 times 12. Let's just get the calculator out so we can show you how to do that. This is the calculator that I think it's easy to use, especially if you're going to take the extra class license. You want to think about a calculator. This is the one I use for everything. So I've got zero point 0.2 times 12. Okay, so
It's
here's,
up a little bit higher.
all
There.
righty, how's that? Okay, so I punched in 0.2 times 12, and that equals 2.4. Okay, 2.4 what? Yes, watch. I always play that game with my grandson. Okay, so you look back at the problem, and here's the potential answers. So 2.4 watts is the calculation, is the correct answer. Okay. Now this is the easiest one to do because you already have the pie chart and you know I and E, so it's easy to calculate. This one, take a look at the question. How many watts are consumed when a current of 7 milliamperes, and here's a conversion you're going to have to do.
Oh yeah, I didn't catch
When
that. Good.
there's a couple like this, so where you've got to convert milliamps to amps or kiloohms to ohms, I think. Okay, so I've got a current of 7 milliamperes and a resistance of 1250 ohms. Okay, so let's go back to the pad and see what that's going to look like. Okay. All right. So I got a circuit and it's got a resistance right here. And that resistance is 1,250 ohms. And I have a current, which is 7 milliamps. Milliamps. The little m is for milli. So this is 7/1000ths of an amp. Okay. So I do my pie chart, and it says, okay, I want to calculate power, so it's I times E. Well, here's the problem, because there is an E out here, E volts, but I don't know what it is. Okay, so in order to calculate E, in order to calculate power, I have to figure out what E is first so that I can do this equation. Now, if you look at the book, they'll tell you that the power in this particular circuit is E squared divided by R. Well, how do you know that? Well, you need your other chart here. You need the EIR circle, second magic circle. Okay. So the first thing, the way I would solve this, the simplest way to do it is go step by step and say, okay, in order to calculate power, I need to multiply the current times the voltage. I need I times E. I don't know E, so I'll go over to this circle and calculate E. So in this case, E equals I times R. So first step is E equals I times R. Okay. And we can do, now what's 7 milliamps? That's 0.007 amps. Okay. Because that's the conversion. I have to move that decimal point to go 3 to the left if I'm going up. This is 7 thousandths of an amp. So that's the decimal representation. Okay, so I can do that calculation. I'm going to do it for you a couple different ways. You see this right here? Okay, so let's just multiply 0.007 times this number, 1250, and that equals 8.75. So E equals 8.75. And now, therefore, power equals I times E, which then equals this 8.75 times 0.007. Which is 0.06125. Okay. Let me go back to the answer real quick. 0.06125. Just kind of freeze that, write it down on a little piece of paper somewhere. All right, so let me go back over here to the question and share. You can see on here 0.06125 is not one of the choices. But there's some, and it's not 61 watts. It's probably 61 milliwatts. Why is that true? Okay, let's go back. I'll show you on the pad here. 0.06125 watts. If I want to convert this to milliwatts, I move this decimal point 3 places to the right. So this is 61.25 milliwatts. So in this particular case, I had to convert milliamps to amps by moving the decimal point to the left 3 to go from thousandths to units. And then I took watts and converted them back to milliwatts by moving that decimal point back to the right 3 places. 1, 2, 3. So it's at this 61.2. Okay. Now, as you get more and more comfortable with this, you'll do this in your head. You'll know this is milliamps, and you'll do the multiplication of 7 times 1250, and you'll say, and you'll get the answer in milliwatts directly. But don't do that now because it's all new to you. Just do the conversion, milliamps to amps. Go over here and calculate the E. That's this calculation, gives you 8.75 volts. Then do the powers, I times E, convert these watts back to milliwatts.
Let me quickly show them my chart again. Just let me share a second.
Okay, you should be able to share.
All right. So here, remember when we go this way, we're moving places to the right. So what we did is we went To go from milli to units, we have to go 3 places to the left. If we go to units from milli, we have to go to 3 places to the right because we're coming down the scale. That's all we've been doing here was working in the units and milli and that problem. And all formulas have to be calculated in units. That's a thing to remember. You can't calculate in milliwatts and volts and in different units. They all have to be in units. And so that means if you're giving it in mega, you got to move it down to units. If you're giving it in micro, you got to move it up to units in order to do the problem. Then you may, after when you're done, move it back down again, as you did in this example. Okay.
All right, I'm going to show you something. I'm going to go quick, and if you this is one of these things. If you know what I'm talking about, then you know what I'm talking about. If not, don't worry about it. And on the calculator down here, they've got three. I'll move it up closer so you can see it. See where the 4, 5, and 6 is? This says FLO. That's for floating point. This is SCI for scientific. And this is ENG for engineering notation. And all these things we've been doing with milli and micro and kilo and giga, those are all engineering notations. All the exponents are in threes. So a kiloohm is 10 to the third ohms, and a megohm is 10 to the sixth ohms. And we don't say gigohm, but that would be 10. A gig is 10 to the ninth. So I can set this calculator for engineering notation by pushing the second key, that green key up here, and then over here, over top of the sixth button, says ENG, and I push that. And now you can see up here, it says that I'm using engineering notation. Okay, so in that case, for example, I have the 0.007 amps. If I put in 0.007, and then I'm going to do, my calculation was times R. So I do times, and notice how it switches it to 7 times 10 to the minus 3, or 7 milliamps. 10 to the minus 3, 1,000ths of an amp. Okay. So then I would, and then let me just clear this, and I'll do the calculation here, the I times E. Okay. So I know that I is, I should have left it in. 0.007 is the I. And then we're going to multiply that times E, and I calculated E is 8.75. And I get equals, and there you go. It already tells you that it's 61.25 milliwatts. That minus 3 exponent tells you it's milli. So I just did that fast. You don't have to learn that right now. If you want more discussion about it, or you want to practice it a little bit and ask me questions, send me an email, because it makes it very handy as you get, again, when you get more familiar with actually making these calculations, it'll kind of pop in and say, 61 milliwatts. You won't have to actually make the conversion.
You could actually enter 7 milliamps by putting in 7.
Right. We could go ahead and put it in. I won't go there right now. But so if we go back here, and I've already checked off the answer for this one, 7 milliamps, 1250 ohms, 61 milliwatts. Okay. Now, if you look in the book, you will see that they will give you an equation for this where you know the current and the resistance. They'll say that power is equal to I squared times R. Okay. Now that's basically what I did, but I didn't have to remember that equation. You don't have to remember that equation if you can draw these two circles. You say, I need to calculate the E first, and then I can do I times E to get power. Okay. Essentially, that's what these two equations do. If I took this E equals I times R and substitute it here for E, then I would get I times R, or I squared R. So it's basically, to get to that equation, you do the two steps that I did here. Calculate the E, and then calculate power using I times that E you calculated. The next question is going to be similar, except the missing value is going to be the current. So we'll do that next. I have to kind of get to that. So wait with me for a minute. Let me go to share.
No questions as of now.
Okay, good. Let's see. Review. I'm going to question. We do by chapter. I'm in chapter
B5,
4.
B04, I guess.
Okay. I'm going for B05. Oops.
You want to do it? Did you do it by subunit? That should work.
Yeah, which sub element is it?
G5,
That's
B.
open. G5B. And I went G5B05.
Right.
All right. No, I just did that.
Yeah. Next one is it's
I
B06.
need 4. All right.
Oh, wait a minute. It's B03, 4, and 5.
I need 3.
Okay. Fortunately, you got to start all over to get there.
Yeah, that ARRL site's not always very friendly. All right, here we go. You see my screen, right?
Yep.
How many watts of electrical power consumed if 400 volts DC is supplied to 800 ohms? You can already see the problem. They don't give you I, so we're going to have to calculate it. Okay, so let me do it. I'm going to use my same methodology and okay, so here's a circuit. I've got an R that's 800 ohms. When they say a load of 800 ohms, that's what this means. It's the resistance out here that you're powering up. And we have 400 volts over here. Okay, so P E. Okay, so same problem. They give you the voltage, but they don't give you the current. So I'm going to have to calculate that. How do I calculate current? I use Ohm's law. E equals I times R. All right, so I need I. So I is equal to E divided by R. Okay, so first thing I have to calculate is I equals E divided by R. That's a real easy one because it's going to be 400 divided by 800. Okay, equals 0.5. 0.5 amps. Okay, now I've got I times E to give me power. So power equals I times E. Okay, and I'll draw this in here. I is now 0.5 amps. Okay, so this is easy again. I've got 0.5 times 400 equals 200 watts. Okay, the algebra says that I can substitute E over R for I. Okay, and so therefore the actual equation would become P equals E over R times E, which is equal to E squared over R. Okay, why I do it this way is so you don't have to memorize 3 formulas. All you have to be able to do is draw these 2 pictures. So you don't have to think, oh, okay, so power is equal to E squared over R. I did it without knowing that. I basically, the process was the same thing, but I just did it much slower step by step so that I could, you could do it algebraically. You could just do all of this and get to this equation and then say, okay, so E squared over R is 400 times 400 over 800. I'll just do that on a calculator for fun. So I have 400 times 400, and that gives me 16. And now I've got my engineering notation. Let me switch it back to floating points. So it's 160,000 divided by 800, and there you go. You still get 200. Okay, we'll check that on the exam. And so here's the question, and the answer: 200 watts.
Your next question is 8 and 9 on the same section.
Right. Okay, so this was DC power. Calculating AC power is the same, but you have to make sure that you factor the voltage appropriately, because remember, we have an equivalence that says what's the AC voltage that is what's the equivalent AC voltage to a DC voltage that would generate the same amount of power, and that the AC voltage is called the RMS volt. Okay, so we have to calculate that, and I'll show you how we do it. So I'm going to B8, 3, 4, 5, 6, 7, 8. Okay, so what is the peak-to-peak voltage of a? Oh, this is even easier. I thought this was a power question.
Well, it sort of is because you're going to need it for.
By the way, this question is shown on page 4-6. There's 2 questions for AC power. Okay, this is even easier. All right, so you see, I've got a peak-to-peak voltage of sine wave, and the RMS voltage is 120 volts. All right, so let's go and show you what that looks like. There's a sine, and what I'm going to tell you right now is only for sine waves, so keep that in mind. So here is one cycle of a sine wave, okay? And there's three voltages. The the peak voltage, I'll just call that V peak, PK, so you can see it well, is the top of 1/2 of the cycle here, from 0 to the maximum amplitude. That's called the peak voltage. The other voltage that you see is from one top to the maximum bottom, and that's V peak to peak, from this peak to that peak. And it should be clear that V peak to peak is equal to 2 times V peak. Okay. So then we talked about there's this equivalent voltage that provides the same amount of heating as a DC voltage, and that's called the RMS voltage. Let me just draw this line here for VRMS. Okay. And this is only true of a sine wave. If you have a more complex waveform, the VRMS has to be measured with some kind of special meter. It's hard to calculate. So the VRMS is equal to 0.707 times V peak, okay? Or V peak is equal to, if you do the math, 1.414.
4, yeah.
I never get that detailed. 1.414 times VRMS. And then to get V peak to peak, you would have to multiply that times 2. So that's actually what they want us to do, is V peak to peak is equal to 1.41, 2 times 2 times 1.414 times the RMS. Okay. If the 0.707 and the 1.4 are the two things that you need to be able to do. The peak is 1.4 times the RMS. And the RMS is 0.7 times the peak.
That's because 1 over 0.707 is 1.4.
Is 1.4. Yeah, you can flip it, do the 1 over, and you get the math. Okay, so the peak-to-peak voltage in this case, I'm sorry, the RMS voltage is 120. So I'll put in 120. So that's where this dotted line here is, it's 120. And they want to know what's the peak. So I take 120, which is VRMS, I'm going to work backwards here, times 1.41, messed up. RMS is 120 times 1.414.
But already, it kept your old 120, you're in trouble.
Okay, clear. 120 times 1.414, that's this, times 2, that's this. So it gives me about 340 volts, 339.36. Okay, and actually, that's the choice. If you look at the question here, the choice is 339.4. Okay, so let me go back again and run through it real quick. They give me VRMS. So I need to get the peak to peak. So I have to multiply it times 1.414 to give me the peak. I have to multiply it times 2 to give me the peak to peak. So VRMS times 1.4 times 2 is the V peak to peak. Okay, then the other question is the very next one in the go to B09. What's the RMS voltage of a sine wave with a value of 17 volts peak? I swear, Roll, I thought we had a power calculation to do here. Maybe that's in the extra.
Which one? Well, yeah. Well, there's some P calculations coming up that are going to be using E squared, VRMS squared over R. So then you'll see it when you get to the next ones.
All right, so I'll get to the next question. Okay, so what's the RMS voltage of a sine wave with a value of 17? Okay, let's do that. So draw a new sine wave, right? And it tells me the peak, V peak, is 17, and it says, what's the RMS? Okay, so remember, we said that V peak times 0.707 equals V. Okay, real easy. So we'll do 17 times 0.707, and that gives me more or less 12 volts. Go back to the answer and select 12 volts. So all I did in this case, all I had to do was multiply the peak times 0.707, and I get the RMS. Oh, here's the one. I did. Yeah, okay. I missed when I was writing these down. I didn't write this down. Okay. All right. So here's an AC power problem. Okay, we have what's the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Okay, so let's draw the picture. Well, what page is this one on?
Um, page 46.
Okay,
Oh,
just to
excuse
get
me, page 47.
all right.
Page
So if you're
47.
following along in the book, it's on page 47. Okay. All right. So first off, out here, I said I have a 50 ohm dummy load. Why? Why did they tell you it's a 50 ohm dummy load? It's just a real life problem. The dummy load is what you connect to your transceiver um, in order to test it. So you're not radiating test signals out into the ether, if you will. Okay, so I've got a 50 ohm dummy load, and it's dissipating. I know that it's using 1200 watts. Okay, and back in here somewhere is an AC RF voltage, and that voltage equals pressure. Okay, so here we go again. We're going to use pi, and it asks you what the voltage is. What's the RMS voltage? Okay, so that's this E here, and the when we're calculating AC power, you must use the RMS voltage for this E. So fortunately, they ask us for that, so we don't have to do some kind of conversion from peak or peak to peak from to RMS. So we're looking for the RMS voltage, and so the equation for that, or the solution, is that E equals P over I. Okay, and just like some of the previous problems, we don't know I. We've only been given the resistance here, so we have to go to the Ohm's law side of things and see how we're going to solve this. Okay, so I know I have 50 ohms and 1200 watts. Where am I going to go here? Remember that I did the equation. Remember, I'm looking for E, and it equals I times R, but I don't know I either. So what I have to do in this particular case, if you remember the equation I did previously, um, I had the equation that power equals E squared over R. Okay, so in this particular case, I take R times P equals E squared, or square root of R times P equals E. Is that how they solve it in the book?
Yes.
Okay, that's that's a P. Let me do this. R times P. Okay, so let me just solve that for you. I'm trying to take you back up here and show you how I got to that. Um, and basically, I never calculated current to solve it this way. Let me think about that for a minute. Anyway, so let's see. I have R times P. So I have 1200 is the power times 50 ohms is equal, that gives me this number of 60,000. Then I have to take the square root here. And the key for square root is on this calculator is right here. See where it says square root of X? Hold it up a little bit. Right there to the left of my thumb. So I'm going to push that button and I get approximately 245 for the E. And again, that for AC power, that is VRMS. So that's the answer. I don't have to convert it to anything else. Sorry, my phone keeps beeping here. Let me turn that off. All right, so I'll go back to the question real quick. And answer B, 245 volts. So the RMS voltage is 245.
I don't think there's any way to do it and get an intermediate answer. You have, I think this is the way you have to do it.
And I think you're just going to have to remember. I'll play with that, and if I can figure out a simple way to recall it, I'll
What you have
send
to
this
do
out.
is say I equals E over R, but you don't know what they are, so then you have to multiply E over R times E, and you get E squared over R. That's all you can do because you don't know E. There's no way to calculate. You have you have enough information to solve the puzzle, but you can't solve
So
it all by itself.
so you've got basically on the left side here. You're trying to solve for E, so you need P and I. Okay, you don't have I. So now you go over here and you say, okay, what's I? And it's E over R. Okay, so if I go back over here and I say power equals I times E, okay, therefore, I'm going to flip it around here. E equals P over I, okay? I divided both sides by I, so, and then I flipped it around. So E equals P over I. Okay, I, back up here to this guy, I equals E over R. So this equals P divided by E over I.
E over R.
I'm sorry, E over R. Okay, so that equals P. Well,
Multiply
uh,
both sides by E over R. Probably the easiest way to do that.
yeah, it's probably the easiest thing. So um,
It would have been easier to substitute it up in the original equation and then use the power equals I times E, and then E is equal to IR, or
yeah, and
I is
then
equal
do
to E over R
manipulation.
in that
All
case.
right,
I
I'm
is
not going
equal.
to spend any more time on it right now. I'll write it out and send it to you. How the algebraic is,
It's much
but
easier if you just remember that formula.
I remember E squared over R for this. If you get this particular one, you say, okay, E squared, power equals E squared over R, and then manipulate it so that you know that you have to take the square root of R times P.
Nothing you did is wrong there, but it's a
Just
little.
I got kind of bogged down in how we could make it similar. Okay, so let me share the last one here. This is another AC power question, and it says, what is the output peak envelope power of 500 volts peak to peak across a 50 ohm load? Okay, so um, once again, you've got a power equals E squared over R situation. So that's good because that's the only thing. I was worried that you'd have to remember multiple equations. Okay, so let's go back and remember this equation. Power equals E squared over R. So we'll go.
It's probably worth talking about peak envelope power there. It's just confusing. I mean, for this problem, you can
Ignore
ignore.
PEP. Ignore PEP. Okay, so I have 500 volts and I have a 50 ohm load. That's supposed to be ohms. Okay, and remember, we said power equals E squared over R. Okay, so I'll just square this and divide it by R and everything will be good, right? Who says right? No, because remember, this said this is 500 volts peak to peak. Okay, and I can't use peak to peak voltage to calculate power. When I'm doing AC power, and again, it has to be a sine wave, but this is like a pure RF signal of some sort. I have to convert this to an RMS voltage. So in this case, the VRMS is equal to V peak to peak divided by 2. Remember, peak to peak is this voltage. And I want half of that. So I've got to do V peak. So I take V peak to peak divided by 2 times 0.707. That'll give me this voltage here, VRMS. Okay. So in this case, that's going to be the peak to peak is 500. So it'll be 250 times 0.707, which is well, about 200. 250 times 0.707. Oh, it's lower than that. It's 176.75. And now power is equal to E squared over R. So let me just take, and I do have a squaring button here on my calculator. Right there it says X squared. So I'll just square it. So 176.75 squared is this number. And then I'm going to divide by R. I divide by 50. There's 50 ohms. And that tells me I've got, okay, and I'll just do this. I had 176 squared divided by 50 equals 624.8. Okay, roughly 625. And if we go back to the question in the book, that's the right answer. Okay, so what I had to do here is I had to take this 500 volts peak to peak and convert it to VRMS, divided by 2 and multiplied by 0.707, and then square that, E squared over R, to get and divide by 50 to get the power. Sorry, the power. The fact that it says PEP, peak envelope power, for this question, you don't care about that. You just want
All
the
it
thing
really
here.
means is that it's sort of meaningless in a way, because all peak envelope power means is what is the power when the voltage is the highest. Well, it's
Yeah.
the highest, but all you've been given is the highest, so it doesn't matter. That's all peak envelope power means. Once the voltage at the highest it ever is. What's the power when at the highest it ever is? Peak
So
envelope.
two things you need to remember here. You gotta be able to visualize this, that the RMS voltage is the peak to peak divided in half times 0.707 to get that number. And then power equation is E squared over R.
And something not to be misled is peak envelope power. You can never calculate power with anything but RMS. Even peak envelope power is RMS power. I know that sounds ridiculous, but that's the case. Peak envelope power is RMS power. All power is RMS power all the time. It's just the power at the peak of your voice, the power at the peak of your signal, but it's still the RMS power at the peak. Power is RMS always. So this PEP's in there if you to throw you kind of, if you think it means peak voltage peak. It does not. It means it's not related to that at all. It's talking about the peak of your voice.
All right, I'm gonna share screen here. I'm gonna have to
You got 6. Did you do 6?
Is there a 6?
There's a G5, B6, and 14.
But they're not calculations, right?
Yes, I think they are. Yes, they are.
Oh, okay.
G5, you have to back up. We can do 14 next, then you can back up and do.
This
I
is,
could read it to you if you want to save some time. Or
I
you
got
can,
it. No, I pulled it up. I got it. You see that?
yeah.
Okay, so what's the peak envelope power produced by 200 volts peak to peak across 50 ohms dummy load? So um, let me draw the circuit.
Again, it's RMS, right?
I didn't have this on my list. I'm glad you're here to tell me because I would have skipped this. Okay, so I have 200 volts
Peak to peak.
peak to peak. And then out here I have a 50 ohm load. Okay, so once again, power equals, it's the same calculation, E squared over R, but I have to take, this is not the right E. Okay, so I got to get VRMS. So VRMS equals V peak to peak over 2 times 0.707. Okay, so we'll do it. I'm going to kind of zip through this one because we just did the other one. Okay, so the V peak to peak is 200. So I take 200 divided by 2 times 0.707, and that means the RMS voltage is 70 or 70.7. Now I'm going to go to this equation. Power equals E squared over R. So I've got the right voltage now. I've got the RMS. So I square it with the X squared button and divide it by 50. I did the wrong thing. Let me start over. Can I just put 50 and get the answer? Yeah. Okay. So this is equal to 70 squared divided by 50, which is, what, 4,900 over 50 equals about 100 watts. And on my calculator, when I did the exact numbers, I got 99.9 something. Okay, so let's take a look at that real quick. Okay, 200 volts peak to peak. So I converted that to RMS, which is made it about 70, 71. Squared it and divided it by R, and the answer is 100 watts. Okay, there's one more, 14.
Yeah.
Okay, you can almost do this in your head now, right? So what are we going to do? What's the output PEP of 500 volts peak to peak across 50 ohms? Okay, so 500 peak to peak, so I've got to say 500 divided by 2 times 0.707, square that and divide it by 50. So let me go ahead and do the picture. What's the difference here? Now this is 500. Okay, so I'm just going to smash it out on the calculator. Clear. So I've got 500 divided by 2 times 0.707. So that's the RMS voltage.
Don't forget to hit the equals there. It's always a good idea.
I did, I think. Yeah, good. So the RMS voltage was calculated by taking 500 divided by 2 times 0.707. That gives me this, 176.75. Now I'm going to use E squared over R to get the power. Ignore all that over there. So E squared, I'll take that number there and hit X squared. Okay, and then I'll divide by 50. And it's about 625 watts. There's a decimal point, you can sort of see it in there. So let's go back to the question. And I've got 625 is the right answer. So I took 500, which is peak to peak, divide by 2 to get peak, times 0.707 to get RMS, square it, and divide by 50. Once again, the equation you got to remember, and I've doubled the number of things to remember, but it is E squared over R is the power. Okay, we all good?
No questions.
All right, now I'm going to cover series and parallel circuits, and that starts around page 4-17 in the book. And the sequence of questions is in G5.
G5C. G5C. I have the numbers for you if you want me to just remember them for you.
I got them. And I want to start with G5CO3. Even though this is a little bit out of the sequence of the book, but let me just do it this way anyway. Okay, so G5CO3 has 3 resistors in parallel, and they're different values. They're 10, 20, and 50 ohms. Okay, but remember one thing, the total resistance or the equivalent resistance will be less than any of those individual resistances. So the answer is going to be less than 10. Okay, and I'm going to draw a picture and show you why that is. Okay, so let's go to the drawing, and I'm going to out here I have some kind of voltage, but I don't really care about it. So I'll just put it, that's a V, not a Y. I don't really care about that because what I'm saying is I want to look in and say, what's the R equivalent of this circuit? And we have, firstly, a 10 ohm resistor. Okay, so if I just had 10 ohms, I'd have some current coming along through here, and based on whatever the voltage is. Now they say, okay, I'm going to add another resistor in parallel, and that's going to be 20 ohms. Doesn't matter what it is. So by adding another resistance, I'm going to have more current flowing through the circuit. I've already got my current going through the 10 ohms, and that doesn't change because it's only dependent on the voltage out here. So that current is that current. When I add another resistor, it's going to draw its current for I times R to give you that voltage. So basically the R equivalent is now going to go down because I'm adding more current, or another way to look at it is I'm adding more conductance. So it's like going from a single hose and then suddenly putting in 2 hoses. The water in this part of the hose up here on the top is going to have to increase to support the flow through 2 legs at this point. And if I add yet another leg, and in this case they tell you that that one's 50 ohms, I'm going to get yet more current going through this thing. So out here where I'm looking in at the input, as the current is going up, again, E equals IR, right? So that says that if the voltage stays constant and the current is increasing, then the equivalent resistance must be decreasing. So as I add more resistors in parallel, I get more current or more conductance, and so the overall equivalent resistance is going to be less than any of these. So I already know the answer is going to be less than 10 ohms because the effect of these 2 out here pulling more current. And again, the equivalent resistance, looking in on the left. This is still 10, this is still 20, and this is still 50. And they're each pulling the amount of current that it will take I times R to get this voltage. So one way to look at this is that I'm adding conductance. And the symbol for conductance is G, so I'm adding G plus G plus G. So the G out here, total conductance, is equal to this conductance times this plus this conductance plus this conductance. And G is the inverse of the resistance. So the R equivalent out here, G is 1 over R, and this is 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors you have. Okay, so the adding the conductances by having more current flowing through all these legs of the circuit, that's what you're actually calculating. And you say the equivalent of conductance is the inverse of resistance. So 1 over R plus 1 over R plus 1 over R equals the total 1 over R. All right, so in this case, I've got 1 over 10 plus 1 over 20 plus 1 over 50. Okay, and I'm going to do it with decimals. So this is 0.1, this is 0.05, and this is 0.02. Okay. You need to see that. And I'll turn this on, so I'll say I've got 1 divided by 10 is 0.1. That's the first. The next one is 1 divided by 20, 0.05. And the next one is 1 divided by 50, 0.02. So if I add those up, then let's start with that. I'll say 0.1 plus 0.05 plus 0.02 equals 0.17. Okay, but remember that's 1 over R equivalent. That's the conductance. So I've got to do the inverse of that, and they talk about that where you do the inverse of the inverses. So now I've got 0.17. I've got a 1 over X button on my calculator. You see that right there? I'll just do 0.17 and do the 1 over X, and you can see it's like 5.8882 ohms. Again, it's less than 10, so I know if I got like 58 or something like that on here, I know I made a mistake because I know the answer has to be less than 10. Got to be smaller than the smallest number. So I'll just go back to the choices here, and remember I had 5.88, basically 5.9 ohms. So I'm adding the conductances, which is to say the inverse of the resistances, and then I invert that back to get the equivalent resistance looking in at the input. Okay, so here's the next one. This is a 100 ohm and a 200 resistor in parallel. Flip my notebook open. Okay, so here's my circuit. My resistors are squiggles. Those are resistance. Okay, so here's 100. Here's 200. Okay, so when you have two resistors in the book, they give you this. It's the same equation. So R 1 over R equivalent, or sometimes they write 1 over R total, is equal to 1 over R1 1 over R2. And if you do all the algebra on this, there's another equation that says that this is equal to R1 times R2 over 1 plus R2. And you do that by multiplying R1 over R1 and R2 over and to do the algebra to simplify it down to this equation. Okay, so if you want to do that, that's fine. So then you'd get 100 times 200 times 200 is equal to 20,000. And then I messed up here. Let's just put this up here. 20,000. So, and underneath here, I'm going to have 300. So let's just divide by 300. It's simple. So that tells me it's about 67 ohms. I feel good about that because it's got to be less than 100 or 200. Okay. If I did it the way we showed before, the complex way would be 1 over 100 plus 1 over 200, 1 over our total or equivalent equals this. So this is 0.1 plus
No, 0.01.
I'm sorry, 0.01 and 0.005, right?
Yeah.
Okay, so now I've got 0.015, but then I have to do 1 over 0.015 to get that R. So 0.015 and 1 over X, and I got the same answer. I got 67. Okay. This R times R divided by R plus R is a simplification of this equation up here.
That only
Okay, so
works for two values, though.
it
So
only works with 2. So if you've got 3 or 4 or whatever, you have to do it this way. Okay. So 67 ohms is the answer. We'll go back to the question. And that's that. See, that's C4. Again, I'm going to do 8 next with 2 capacitors. This is covered in the chapter. Is covered towards the end, but I'll do it this way just because it's in sequence. So you've got 2 things that you have to worry about here. You've got 2 5 nanofarad capacitors and 1 750 picofarad capacitor, and they're all connected in parallel. Okay, so take a look. 5 nanofarad and 2 5 nanofarad and 1 750 picofarad capacitor. So let's go to the tablet and I'll draw you that. They're connected in parallel. Take a lot of space. So here's capacitor, capacitor, capacitor. 5 nanofarad. 5 nanofarad. I guess that should be a capital looking thing there, right? And 750 picofarad. Okay, so a nanofarad is a 10 to the minus 9th, and 10 to the minus 12 is picofarads. Okay, so somehow I got to make all these things equivalent. They've all got to be in nanofarads or picofarads. So I'm going to choose to make them all picofarads. So I'm going to go from nano to pico. So I'm going to move the decimal point to the right 3 places. So this is 5,000 picofarads. This is 5,000 picofarads. And then this is 750 picofarads. Okay? And they're connected in parallel. So capacitors in parallel are the same as resistors in series. You just add them. Why is that, Tom? And the answer is because of the capacitive reactance is inversely related to the capacitance. You don't have to remember that answer. You just have to remember the capacitors in parallel add like resistors in series. Capacitors in parallel add up like resistors in series. So it'll be 5,000 plus 5,000 plus 750. So that will be 10,750 picofarads.
Just for fun, how many nanofarads would that be?
So how many nanofarads that is? Okay, to go from pico to nano, you're going from 10 to the minus 12 to 10 to the minus 9. So that will be 10.75 nanofarads.
Now, see, the answers are some of them are in nanofarads and some of them are in picofarads, and you don't know
Right.
which.
Let's go back. Let's go back to the answers, and you'll see why this is a big deal. So, sure enough, the right answer is given in nanofarads. We've got nanofarads, picofarads, nanofarads. Now, on the one hand, you'll say, well, it must be this one because I got the 10750. But it is, in fact, 10.750 nanofarads or 10,750 picofarads. So you have to remember two things. First off, convert it so everything is in the same unit, nanofarads or picofarads. And secondly, capacitors in parallel add. Capacitors in series, you have to calculate it the same way you do resistors in parallel. Okay, that's 8, right?
Yes.
All right, so the next one is 9. Aha! 3 100 microfarad capacitors connected in series. So what I just said about parallel being additive, it means that in series you have to do the inverse of the inverse. Okay, so let me get to that. I had 3 capacitors in series. So for capacitors, the capacitor equivalent is 1 over that, I'm sorry, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. It's helpful here that they're all the same. So this is 100 microfarad, and this is 100 microfarad, and this is 100 microfarad. Okay, so I got 1 over 100 plus 1 over 100 plus 1 over 100. So that's going to be 3 over 100, and that's 0.03. Okay, so you can do this either way. You can say, okay, so remember I got to invert it again. So the C equivalent is equal to 100 over 3, or 1 over 0.03. And you can see that these are the same thing. If you move the decimal point 2 places, it's equivalent. So, and the answer, I don't have to use a calculator. It's going to be 33.33. Okay. Now, it happens that when you have all the capacitors in series are equal, then the total capacitance is just the value of 1 divided by how many you have. So if you said, oh, and that's what we did here. But the simplification of it, you can look at this really quickly and say, okay, I've got 300 microfarad capacitors in series. So it's 100 divided by 123. So that's equal to 33.3. And you do the same thing with resistors, and maybe I think we'll have a problem with that. If I have a 100 ohm resistor in parallel with another 100 ohm resistor, in parallel with another 100 ohm resistor, the equivalent resistance is 33.3. So if they're all the same, take the value and divide it by how many there are, and that's the equivalent resistance. That's a simplification of this math down here. Okay, so let's go back and look at remember 33.333 is the calculated answer, and it was microfarads. We didn't have to change anything, so 33.3 microfarads is the answer. Remember, capacitors in series, you have to do the inverse of the inverse because, again, the reason I explained earlier.
So you might want to do G5C12 next. That's a 20 and a 50 in series.
So I got 10, 11, and 12 to do.
Yeah, I just thought you might want to do the other capacitor one first.
All right. Okay, so I've got a 20 in series with a 50.
Flip your pictures.
Time is getting to be.
Flip your screen so you can see the big screen.
You're seeing this, right?
What? You're seeing the question, but we're not seeing the. Oh, okay. You're doing it your way. I'm fine. Go ahead.
Okay, so I've got 20 and 50 in series. And they're both microfarads. And don't fall into a trap. Don't say, oh, they're in series, add them, because they're capacitors. So you have to do the inverse. So 1 over C equivalent is equal to 1 over 20. And notice I left out the microfarad part. I know I've got microfarads, so I'm not going to write 20 times 10 to the minus 6. I just keep that in my head. As long as I know that everything is the same units, I can kind of ignore it as long as well, I'll have to look at, yeah, the answer will be in microfarads. So I've got 1 over 20 plus 1 over 50. Right, so this is 0.05 plus 0.02, which is therefore 0.07. Then I have to invert it. Take 1 over 0.07. And there's 0.07 and 1 over x, see that button right there. It gives me about 14. 14.3 microfarad. Okay. Now, in the book, it'll give you that other equation thing where it says you can do C1 times C2 over C1 plus C2. So if you want to go ahead and do that, so you get 20 times 50 will be 1,000 divided by 70, and that's this. So you get 14.3 that way too. Go back to, I have to find my unshare here. Sorry, I got to share. I think I shared the wrong thing. Should we see it? There we go.
Got it.
Okay, so the calculated answer was 14.3 microfarads. And again, when you're looking at this, you say, okay, 20 microfarad, 50 microfarad, all the answers are in microfarads, so I'm good. I don't have to do a bunch of conversions to picofarads or something like that. Before picofarads were invented, they called them microfarads or Mickey Mikes. so at least you don't have to deal with that. All right, so this is 12. I got to go back and do 10 and 11. Did I do 9?
Yes, 300s in series. You did that one. 300 puffs in series. Did you do that? Yeah, you did. There was 33 and The third.
Yeah, okay, right. All right, let me just reset this a minute. So I'm in G5, C, and I'm going to go to, I didn't do transformers yet. We'll do that in a minute.
10 and 11, and
All right, so 300 mics in series was 33.3. We did that one. Okay, so now I've got inductors in parallel. Okay, so we did resistors in series and parallel, capacitors in series, parallel. Now we have inductors. So inductors are the same as resistors. Okay, and I'm not even going to do the calculation here because notice that I have three 10 millihenry inductors in parallel. So they're all the same. So um, I've got 10 millihenries is the value of each one, and there's three of them. So the answer is going to be 10 millihenries divided by 3. Okay, and the answer then is 3.3 millihenries.
well, I always tell people to remember the formulas for resistors and inductors are the same, as that their symbols almost look the same.
Yeah, that's a good point. So the next question will give me a chance to do some drawing. So that's 10, and then here's 11. Inductance of a circuit with 20 millihenries connected in series with a 50. So let me just go ahead and draw that one. It's because it's easy. Look at the bleed through of my carbon.
Good thing you had that.
That's not a coincidence. All right. So I've got a series circuit and I got my inductors. And again, like Roll said, when we draw resistors, we draw them like this. So if you need a little visual thing to remind you, notice they kind of look the same. So I'm going to put two inductors in series. And of course, there has to be a wire coming back. So then I've got an L equivalent that I'm looking at. So the inductors are the same as resistors. So I've got 20 millihenry, and I've got
50.
50 millihenries, and and with series, L equivalent is equal to L1 plus L2 plus da 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 da. So it equals 70 millihenries. And we'll go back to that question, and the answers are all given in millihenries, so we don't have to do any thinking on that. 50 plus 20 is 70 millihenries. I, I just wet my whistle here a minute. I got about 6 more questions to go through. And I'm not going to rush. I know we're over time. If you've dropped out because your eyes are glazing over to catch the rest on the recording, that's cool. So let's see, I'm going to just erase all this so that I make sure that we don't lose anything. And I'm going to go, the first one I'm going to do is G5CO6. And this is a totally straightforward thing. You've got a transformer with a 500 turn primary and a 1500 turn secondary, and I put 120 on the primary. So I'm going to get my picture. I'm in the flight path of the Naval Air Station here at Jacksonville, so it's not as bad as the BWI flight path, but every now and then, and it's cool. There's P-8 anti-submarine warfare planes based here, So they were doing touch and goes earlier yesterday afternoon. Actually, it was fun to watch. Okay, so I've got a transformer, and let's see, it's 500 on the primary and 1500 on the secondary. So I'm not going to draw 500 turns, but this is 500, and it's kind of N primary. And over here, there's more. Typically on a schematic, they don't draw that. They just draw both sides the same. So I'm drawing it just to give you the idea of what's going on. So on this side, the N secondary equals 1,500. Okay, so N is the number of turns, and this is the number of turns, or some equivalent ratio. So the ratio is there's 3 on the secondary for 1 here. So I'm just going to say that that's a 3-to-1, where that's the secondary NS to NP. Okay, and they say I'm going to put 120 volts over here, AC. It won't work on DC. This is the whole basis for all electrical transmission right now. And what in fact is in reality happening is the other way around. Out on the pole outside your house, there's a big primary, and there's like, I don't know, 13,000 volts on it, and then it steps it down. But in this case, this is a step up. So the voltage is directly related to the ratio of the turns. So it's 3 times as much voltage over here as there is over here. So this is going to be 360 volts. So the turns ratio is 3-to-1. The voltage ratio is 3-to-1. Just as an aside, the current ratio will be the opposite because you have the same, theoretically rather, you have the same power on each side of the transformer. So if there's 3 times the voltage, then on this side there's only 1/3 the current. They don't ask you that anywhere, but that's, so conceptually you should know that the amount of power is the same. So the E times I has to be the same on both sides. Okay, so that's your answer. It's 360 volts when the primary to the secondary. The secondary is 3 times the primary. And so I'll go back to that real quick. Try to go back to that. I just lost my cursor.
This is page 415 if anybody's looking.
Oh, yeah, good. Thank you. It's point 415. Okay, so what did I say it was? 360? There you go. Okay, so this is the way transformers work. Primary and the secondary, and it's 3-to-1. The other question they give you, I got to go back to the main because I skipped over it a minute ago. E5C2. So it says, all right, what's the output voltage if an input signal is applied to the secondary? What's the output if an input is applied to the secondary winding of a 4-to-1 voltage step-down transformer instead of the primary winding? Okay, so let's visualize what that's all about. Okay, so it's a step-down transformer. So again, you wouldn't see this normally in a schematic, but the windings are like this. There's the ratio is 4-to-1. Typically, this is the primary, and this is the secondary, and they call it a step down. So if I had 120 volts on this, I would have 30 volts on this side because it steps the voltage down. Or I could have 14,000, and then whatever hundreds would be on this side. So a typical step-down transformer is going to look like this. More windings on the primary than on the secondary. So that's the ratio. It's 4 times. The voltage here would be 120, over here would be 30, or whatever that, whatever you put into it. So now the question says, well, what if I did this? And I put, now my ratio is 1 to 4, just like it was when it was right side up. And I'm going to use the secondary, and I'm going to put some voltage, V. They don't tell you how much it is. Okay. So when I configure it this way, if I put a voltage on this input here on the secondary, because of the 4 to 1 winding, the voltage out here is going to be 4V. Just like, when I had it this way, I had 120 and I got 30. Well, I could do it the other way around. I could put 30 here and I would get 120 here. So, it's basically the input voltage times 4, because you've basically turned it upside down and made it into a step up transformer. So that the choices. Somebody someday is going to have to help me if there's like a hotkey to switch from camera to share, that I don't have to keep moving my mouse around and clipping on things and whatever. But if you know the answer to that, send me an email. All right. So it was a step down, but I reversed it. So I'm putting the voltage into the secondary. So therefore the input voltage is multiplied by 4. So if you get this question, read it really carefully and see, okay, they're just reversing it. So instead of being 4 times, I'm sorry, 1/4, because it's stepped down, it'll turn into 4 times because you've reversed it and you're making it step up. All right, the last, I'm going to do G5CO7. It's a transformer question. We can use a transformer to transform voltage, and we talked about how when the voltage goes up, the current goes down. So you can also use that transformer to change impedance. So here it says, if what transformer turns ratio matches an antenna 600 ohm feed point impedance to a 50 ohm coaxial cable. Okay, so what would be the turns ratio required for that? Okay, let me go and draw a picture of what we're talking about. So you got my paper upside down. All right, so here's a transformer, and I'm trying to turn, on this side, I go out to an antenna of some sort. I'll draw a sort of a balance thing here, okay? And on this side, the antenna is 600 ohms. And this side, it's 50 ohms. And how I know that, this is V over I, right? So the voltage across here divided by the current gives you 600, and over here the voltage times current gives you 50. Okay. Now, I could do all this V times I on this side equals V times I on this side, and I won't bother with all that, but the basic situation is that the turns ratio of the primary to N secondary is equal to the square root of the Z primary. This is Z, it's impedance. Z is like R, okay? Z primary over Z secondary. Okay? I'm not going to derive all that, but it has to do with the fact that V times I on this side is equal to V times I on this side. So if you use the V over I and substitute with the V times I, you'll get this equation. Okay, so in this case, um, um, by the way, it doesn't matter about the primary and the secondary. So all we have to do is it's 600 divided by 50, because we always want that number to be positive. You don't make it into a, remember we were doing SWR and we talked about how it's always more than one. Same case here. So I need to take 600 divided by 50 and take the square root. So the answer is the square root of 12. And I take 12, and I got the square root. So the number is 3.46. Okay, so the turns ratio is all they ask you about. They don't tell you how many turns on each side. And the answer is 3.46, and actually selections are like 3 point. The answer is 3.5. Let me show you some. What page? This is on 4 dash what? 4 dash 24. I don't know if this is picked up in the errata, but when they do the example in the book on page 4 dash 24, we've got a mistake here. It says 600 divided by 500. It should be 600 divided by 50. So it's example 37 on page 4 dash 24. If you don't check your book, that number should be 50. Okay, so I'll go back to the question in the book. Of course, they trick you because you do 600 divided by 50 and you get 12. Oh, that must be it. And it's not. It's this. It's the square root of 12. So just do the two impedances, the bigger over the smaller, and take the square root. And you got the right answer. Okay. Now I got three more to do, and roll. I don't know if there were any others, but I'm going to do the three antenna calculations, and then if you want to, if there's something I missed, then we'll look at that.
Well, I mean, the only other ones is SWR given the load impedance and the transmission line impedance is pretty
Yeah,
good.
and those are so trivial that so there's some antenna calculations in G9B and G9B 10, 11, and 12. Oh, I skipped 10. All right, let's try this again. Went too fast. G9B. G10. Okay. Approximate length for half-wave dipole antenna up for 14.250 megahertz. All right. So this is a half-wave dipole. So this is like a wire hanging out of a tree, or maybe you made it out of some aluminum rod and stuck it up on top of a little mast on your roof, some such thing like that. And uh, remember, it's a half wave, 14,250 megahertz. Let's draw that. So, and I'm just gonna show a center fed thing here. So here's this the length of this is about a half wave length. Okay, that out. and the frequency is 14.250 megahertz. Okay, now you can do all kind of calculations here with um, lambda equals c over frequency, where what lambda is wavelength, frequency is frequency, and c is the speed of light. Okay, so lambda in this case would be speed of light is about 3 times 10 to the 8th meters per second, and frequency he gave us that is 14.25 megahertz, so it's 14.25 times 10 to the 6th. And if we do that, then I'm going to simplify it a little bit, and it's going to be 300 divided by 14.25, and that's going to be 21 meters. Okay, this formula is in meters. Notice, by the way, we say this is in the 20-meter band, and that's why I'm kind of showing you this. If it was 15 megahertz, it would come out to be exactly 20 meters. So, in fact, all the ham frequencies in the quote unquote 20-meter band are actually a slightly longer wavelength. Just something to remember that we're never exactly exact between what we call the band in meters, how we name the band, and the actual wavelength of the signals. Okay, so you can keep going. You can then divide this by 2 and then convert meters into feet and get to an answer. But there's no need to do all this. We have a rule of thumb for a half wavelength antenna that says that the length in feet is equal to 468 divided by the frequency in megahertz. Use this number. The book has a different number. Don't use the number in the book. Use this number. Okay, so in this case, I got 468 divided by 14.250. And it's about 33 feet. Okay? And I'll show you that that's the right answer in a minute. Just keep in the back of your mind it's 33 feet. The book, and we roll into an explanation of this. It turns out that there's a more precise number that you can use for this, but in terms of rule of thumb, 468 is easy to remember. The test questions are based on using the number 468, and that's what you should use to pass the test. When you're actually building an antenna, the other number, what is it, 492 roll, will give you a more accurate answer. But you're building an antenna, you say it's 33 feet, just make it like a foot longer or so, 2 feet longer, and then you can shorten it up to get the lowest SWR. So
You always should make it longer because you can just wrap it back around
right, you can
to make it
shorten it. You don't
square.
have to cut it to shorten it. You just bend the wire back on itself and wrap it, and it'll work just fine. So since it's getting late, I'm not going to extend the discussion about it. But for a dipole, a half-wave dipole, use 468 divided by the frequency in megahertz will give you the length in feet. Now, to check yourself, and you should be thinking like this isn't just a math problem. you're saying, okay, 14.250 megahertz, that's in the 20-meter band. Okay, you should know that. 14.250, that's in the 20-meter band. That's something that every ham knows. Exactly what frequencies you're allowed to use and all that, you can have a chart up on the wall, but you should know the 14250 is in the 20-meter band. Okay, so a half wavelength at 20 meters, the half wavelength is going to be 10 meters, right? And a meter, 1 meter is about 3 feet. A little more, but close enough. Engineering approximation. Okay. So a 20-meter dipole should be about 30 feet long. Now, it's not really 20 meters and it's not really 3 feet. So 30 feet is not the right answer, but it tells you what the answer ought to be. Okay. So when you go and you actually look at the question, what are the choices? 8, 16, 24, and 33. Well, we actually calculated 33, and that's the right answer. In my head, I said, oh, 14,250, that's 20 meters. Half of that is 10 meters. 10 meters is about 30 feet. There it is. Close enough. And it's far enough away from 24 feet that I'm confident that's the right answer. So, yeah. And you don't have to answer the question that way. You just do the calculation, but in your head look and say, okay, I think the answer should be around 30 feet. And then you look at it and, that kind of confirms that your calculation was okay. Okay, the next one is a half-wave dipole for 3550 megahertz. Okay, so let's look at it first here. So this is in the 80-meter band. Okay, so that tells you the antenna is it's going to be a half-wave dipole. So it's half of 80, which is 40 meters, which is going to be in the neighborhood of 120 feet. So I'm already guessing that the answer C, 132 feet, is going to be the right answer. Let's go ahead and calculate it. Okay. Half wave, and over 2. And this is for...
These are pages 7.4 and 7.5, by the way.
Oh, thanks. Yeah, page 7-4 and 7-5. Okay. So the formula, I want you to remember this. This is really hard. 468, right? 468. 468 divided by 3.55. Remember, that's for a half wavelength. The next question will be a quarter wave, and it'll be obvious what that is. You still only have to remember 468. So 468 divided by 3.55, this is in megahertz, frequency in megahertz, will give you the length in feet. Okay? 468 helps to turn it on. 468 divided by 3.55, 132 feet. Remember what I said? I said it was 80 meters divided by 2 is 40 times 3 is 120. So Tom's estimate was 120 feet. Okay. So I already knew the answer should be in the neighborhood of 120, a little bit bigger because of the simplification I used. So the actual answer is 132. We'll go back over to the question, and you can see the choice here is 132 feet. Okay, so remember that the length in feet is it's 468 divided by the frequency in megahertz. Don't convert the frequency to hertz, and don't get confused between feet and meters. Just divide 468 by this number and you'll be good. Okay, the last one asks you for a length for a quarter wavelength antenna. So let me flip back to the picture I just drew. If a half wavelength is 468, then lambda over 4 is going to be half of 468, so it'll be 234. By the way, that's how you can kind of check. Everybody ought to be able to remember 234. And for the quarter wave, it's 234. For the half wave, it's 468. So it's 234, 468. This times 2 gives this. Okay? So it asks you for for the length of a quarter wave monopole antenna, and ordinarily that's some kind of vertical, and it's lambda over 4. Okay, that's the length of the antenna, and it's at 28.5 megahertz. Okay, 28.5 megahertz is in the 10 meter band. You should know this. Okay, so a quarter wave in the 10 meter band would be, just do this over here, would be 2.5 meters. Okay, remember I have to divide this by 4. So 10 meter band, quarter wave is 2.5 meters. I got to convert this to feet, so it's about 7.5 feet. A little longer than 7.5 feet. Okay, let's actually do the math. Remember, quarter wave, so it's 234. Don't use the number in the book. Use 234 divided by 28.5. 234 divided by the frequency in megahertz. Don't convert it. Just remember it's got to be in megahertz. Equals how many feet? 234 divided by 28.5. So this is 8.21 feet. And Tom's estimate was 7.5. So it tells me my math is probably okay because I'm close to what I thought it would be. And I'll go back and check the answer. They don't even give it in fractions. They just say it's 8 feet. Okay, so for a quarter wave, it's 234. 234 divided by the frequency in megahertz. For a half wave, it's 468 divided by the frequency in megahertz. If you use the numbers in the book, it's like 592 or something. You'll get close to this answer, but it won't be the answer that's on the test. If you're building an antenna, I would use the value in the book. All right, which other ones do you have for me to do?
But there's really nothing else. I mean, it's just the G9, A08, 9, and 10 about calculating SWR. When you know the load impedance, and you can talk your way through them without even writing it down, I think.
G9.
G9, 8, A08, 9, and 10.
All right, yeah, this isn't even a math problem. If the SWR on an antenna feed line is 5:1, and a matching network is adjusted to present 1:1, what's the resulting SWR in a feed line? Well, let me draw a picture real quick. At least for the one.
Yeah, this is misleading you to think it's a math problem, but it isn't.
Yeah, but as long as we're here, okay, so I have an antenna. and I have a feed line, and if I right at this point here, I look into this and I measure the SWR, and the SWR is 5 to 1. Okay. Firstly, why is that? It it probably means that the antenna feed point impedance up here doesn't match the characteristic impedance of the coax. I'm sorry, I call it coax. I should call it the feed line. Okay. It could be ladder line. Twin lead ladder line, whatever, window line. So and over here, here's my radio, and I'm going to call it I'll just call it a transmitter, but it's a transceiver probably. So the transceiver right at this point, he's looking for 50 ohms. He wants to connect to a 50 ohm load. If it sees anything other than 50 ohms, first off, you don't get maximum power transfer. Secondly, you could get significant voltages coming back here could hurt the transmitter, so it's got protection circuits to reduce the power. So just like I have at my house, as you've seen my jack, I have a box here, and what they call it in the problem is they call this a matching network. And usually inside here, there's some capacitors and inductors that kind of transform the impedance on this side to whatever the impedance is on this side, vice versa, really, so that the transmitter thinks that it's connected up to a 50 ohm load. So the question is, if I put this matching network, often called, by the way, an antenna tuner, which is really misleading, okay, so if I put this matching network in here so that the transmitter sees 50 ohms, what is the SWR now along here? Okay. The answer is it's still 5 to 1. You didn't do anything to change that SWR out here. All you did was transform it so it looks to the transmitter like it's a 50 ohm load. You still have a 5 to 1 SWR on this transmission line. You didn't eliminate the SWR. That's what they're trying to tell you. You still got it, and may or may not be a problem depending on the loss in your line. But it's not fixing the SWR. It's just matching this mismatch over here, really up here, to make it look like 50 ohms.
So if you had a SWR meter in your transmitter, which most of them do, it would say 1 to 1.
Right back here, if I looked at the SWR, it'll say the SWR equals 1. In fact, I have a manual box to tune this, and that's exactly what I do. I adjust these controls, capacitors, and inductors so that I see an SWR of 1 to 1 here. But on the other side of it, it's still 5 to 1. Nothing changed. And we'll flip back to the problem, and so here you go. So it's 5 to 1, matching network, adjust to present 1 to 1. What's the SWR on the feed line? Still 5 to 1. You didn't change anything there. All right. This is easy. Standing wave ratio. So you've got whatever the impedance of the feed line and the load, whatever the ratio is the SWR, and it's always greater than 1. So 1 to 4 and 1 to 2 are not the right answer. So it's 200 divided by 50, which makes a 4 to 1 SWR. So just whichever is bigger, divide you've got two things. You'll have the antenna, in this case, they're showing a resistive load and a characteristic impedance. It's important for these problems that it's a resistive load. When the load starts looking somewhat what they call reactive, which means it has capacitance or inductance, then it's a little more complicated. So they don't ask you that. They just give you the resistive load. So in this case, I got a 50 ohm characteristic impedance on the feed line and a 200 ohm load, 4-to-1. I think there's one more like this. Yeah, so here's the other way around. So I've got a 50 ohm feed line and a 10 ohm resistive load. Again, it's not 1-to-5. It's still 5-to-1. So it's always put the bigger number on top. So it's 50 divided by 10, 5-to-1. Just for fun, what's the last answer? Transmission line loss on SWR. If you have high loss, it may reduce what you think you're measuring for SWR. So we went through this scenario last week. We said if you suddenly miraculously get an improved SWR, probably suddenly miraculously got a bad connection or water in your coax or something. All right, does that cover everything?
Yeah.
How's everybody like that? Was that okay? Is
That was
anybody
great.
left?
We got no
I'll try.
questions.
I'll try to get the thing with the e squared r just to derive that formula for you. But for those calculations where we had those two problems, e squared over r, you should remember that. I was trying to find a way that you could not have to remember it, but that explanation looks like it's more complicated than just remembering e squared over r.
Okay.
All right, folks. I don't see any more questions. Looks like everybody's happy. If you have something that I didn't do very well, or you would like to talk about it some more, send me an email and I'll see how we can help you. I'm going to stop the recording.